Hello and welcome. Today, we are diving deep into one of the absolute most important chapters for your science board exam, carbon and its compounds.
Yep, we're breaking down Chapter 4 from your NCERT Class 10 science textbook. Seriously, this chapter is packed with concepts that show up on the exam all the time, so you're going to want to pay close attention. Let's get right into it.
So, here's our game plan. We're going to follow the chapter pretty much exactly as it's laid out. We'll start with how carbon forms its special bonds, then we'll see why it's so versatile. After that, we'll hit its key chemical reactions, check out a couple of really important carbon compounds, and wrap up with the cool chemistry behind how soap actually gets things clean.
First things first, let's figure out why carbon bonds the way it does. And the clues, well, they actually start with its physical properties, which are totally different from the ionic compounds you might have studied before.
Just think about it for a second. Ionic compounds, they have these super strong attractions, so they have high melting points and they conduct electricity when you dissolve them. But carbon compounds, they're kind of the opposite. Low melting and boiling points, and they're really bad conductors. This tells us a couple of things. The forces holding them together are weaker, and more importantly, their bonds don't seem to create any ions. So, what in the world is going on?
The whole mystery really comes down to carbon's electron setup. It's got 4 electrons in its outermost shell. Now, to get stable, it needs a full shell, right? So it could either gain 4 electrons or lose 4. But as it turns out, both of those options are a really big problem for carbon.
Okay, look, if carbon tries to gain 4 electrons, its tiny nucleus, which only has 6 protons, would have to hold on to 10 whole electrons. That's just not going to be stable. On the flip side, what about losing all 4 of its valence electrons? Well, that would take a massive amount of energy to pull off. So since both options are basically impossible, carbon comes up with a much smarter solution. Instead of giving or taking electrons, carbon shares them. And this sharing creates a really stable, strong connection we call a covalent bond. By sharing, both atoms get to feel like they have a full outer shell, that stable, noble gas configuration they're all aiming for. This one idea right here is the foundation for pretty much all of organic chemistry.
And you see this sharing happening all over the place. 2 hydrogen atoms share 1 pair of electrons, making a single bond. 2 oxygen atoms share 2 pairs. That's a double bond. And 2 nitrogen atoms, they share 3 pairs to form a super strong triple bond. Then you've got our classic example, methane, where 1 carbon atom shares electrons with 4 different hydrogen atoms, forming 4 single covalent bonds.
So this covalent bonding is cool, but now we get to the really amazing part. Carbon's ability to share electrons is just the beginning. It has 2 special properties, kind of like superpowers, that make it the ultimate building block of literally millions of different compounds.
And here they are, catenation and tetravalency. Catenation is just a fancy word for carbon's incredible ability to link up with other carbon atoms, forming these really long, stable chains. And tetravalency just means that with its 4 valence electrons, every single carbon atom can form 4 bonds. It's this combination that no other element can really match.
Put those 2 superpowers together, and what do you get? An almost infinite variety of structures. You can have long, straight chains of carbon. You can have branch chains that look kind of like trees. And you can even have carbon atoms linking up to form stable rings. This diversity is what makes carbon so special.
But wait, it gets even cooler. Carbon can build completely different molecules using the exact same number of atoms. We call this structural isomerism. Take the formula C4H10, for example. You can arrange those atoms in a straight line, and you get a molecule called butane. Or you can arrange them in a branched shape, and you get a totally different molecule with its own unique properties. Same parts, different structure.
You know, for a long time, people thought these carbon compounds were, well, magical. They believed they could only be made by some mysterious, vital force found inside living things. But then, in 1828, a chemist named Friedrich Wöhler completely changed the game. In his lab, he made urea, an organic compound, from a simple inorganic substance. Just like that, he shattered the vital force theory and kicked open the door to modern organic chemistry.
All right, so we know how carbon builds things. Now, let's talk about how these compounds behave. We're moving on to the key chemical reactions that you absolutely have to know for your exam.
We're going to focus on 4 main types. First, you have combustion. That's just a fancy word for burning. Then there's oxidation, where a compound gains oxygen, like turning an alcohol into an acid. After that, we have addition reactions, where we add new atoms by breaking double or triple bonds. And finally, substitution reactions, where you basically just swap one atom for another in a saturated compound.
Here's a really useful tip for combustion. Saturated hydrocarbons, think of the LPG gas in your kitchen stove, they tend to burn completely, giving off a nice, clean blue flame. But unsaturated hydrocarbons often burn incompletely. This creates a yellow, sooty flame that's full of unburned carbon. That's exactly why the bottom of your cooking pot turns black if the air holes on the stove are blocked and not enough oxygen is getting to the flame.
Okay, let's zoom in a bit and look at two super important carbon compounds that you probably see or use almost every day: ethanol and ethanoic acid.
Let's put them side by side. Ethanol, well, that's the alcohol you find in drinks, hand sanitizers, and even in some fuels. Ethanoic acid is better known as acetic acid, and it's the stuff that gives vinegar its sharp, pungent smell and sour taste, which makes it an awesome preservative. They also have very different chemical personalities, which leads to some interesting reactions.
And here's a big one for your exams: esterification. This is what happens when you react a carboxylic acid, like our ethanoic acid, with an alcohol, like ethanol. When they combine, they form a whole new type of compound called an ester. And esters are famous for one thing: they have these wonderful, pleasant, fruity smells. That's why they're used to make perfumes, food flavorings, you name it.
And for our final section, let's see how carbon compounds help us clean up a mess. We're going to look at the really clever chemistry behind soaps and detergents. The real magic of soap is that its molecule has a split personality. One end is an ionic head that is hydrophilic. It absolutely loves water. The other end is a long hydrocarbon tail that is hydrophobic. It hates water, but it loves oil and grease.
So, how does this actually work? Well, when you mix soap with water, these molecules get busy. They form these tiny spheres called micelles. All the water-hating tails point inwards, grabbing onto any bit of oil or dirt they can find and trapping it in the center. Meanwhile, all the water-loving heads stay on the outside, facing the water. This allows the entire little dirt-filled sphere to be easily washed away.
But soap isn't perfect. If you have hard water with lots of calcium and magnesium ions, the soap reacts with those ions and forms this yucky, insoluble gunk called scum. That's why detergents were invented. They have a slightly different structure that doesn't form scum. They stay effective even in hard water, which is why they're in pretty much all of our shampoos, laundry products, and cleaners today. So when you step back and look at it, carbon's versatility is just staggering. It's the backbone of life itself and countless materials we use every single day, which leaves us with a really exciting question to think about. With its incredible ability to form all these chains, branches, and rings, what amazing new materials, medicines, and technologies are we going to build with it next? And that's it for this explainer. Thanks so much for joining, and good luck with your exams.